we have previously seen, it is sometimes impossible to find an equation for f inverse, even if f is invertible. And so the question is, can I find the slope of the tangent line to f inverse of x if I only have a formula for f of x? And the answer, surprisingly, turns out to be yes. And the way in which we're going to do that is by resorting to the chain rule. I'm going to go ahead and give you the result here. What we're talking about is the derivative of the inverse here. And the inverse function theorem states this: that the derivative of f inverse is the reciprocal of the derivative of f, evaluated at f inverse of x. In other words, going back to our previous graph that we had of f and f inverse, what I'm saying is that if you take matching points here and here that match each other, A, B, and G, and if you draw tangent lines, those tangent line slopes have to be related to one another as reciprocals. And you can see from the graph that this appears to be true. And the reason is really simple. If I take a tangent line and I write its slope as rise over run dur dx, then on the same graph here, this corresponding here will match up with a corresponding dx and dy, just like that. So that the slopes of those two lines are going to be reciprocals of one another. Okay. Now, the proof of the inverse function theorem is delightfully simple. We're going to start with the fact that f of f inverse of x always cancels to give us x back. This is what it means to be an inverse. And if I now take the derivative with respect to x on both sides, then on the right-hand side I get 1. On the left-hand side I have a chain rule situation, outside and inside. My outside function is f, and so the derivative of the outside is f prime of f inverse. And the inside function is f inverse, and its derivative is f inverse prime of x. So that if I now solve by simply dividing both sides by f prime of f inverse of x, I'm done.
So it's a theorem.
Yeah, that's it. It's a theorem. And it's also a derivative rule. The derivative of any inverse is the reciprocal of the derivative of the original parent function evaluated at the inverse. Now, to understand how to use this inverse function theorem, you have to understand the concept of matching points. And that is, if AB is on the graph of f of x, then the point BA will be on the graph of f inverse. If you understand that, then the inverse function theorem is not too hard to use. So let's go back to our function f of x is equal to x cubed plus x plus 1. And I want to observe that f of 1 is equal to 3. Can all of you compute that in your head? As soon as I compute that, then I can immediately write the matching pair equation. F inverse of 3 is equal to 1. I don't have a formula for F inverse, but I do know that F inverse of 3 is equal to 1 for the simple reason that F of 1 is equal to 3. Does that make sense? So now I ask the question, what is F inverse prime of 3? In other words, what is the slope of the line tangent? I know already the point. What is the slope? And to compute that, I'm going to appeal to the inverse function theorem. And the inverse function theorem states that F inverse prime of 3 is the reciprocal of F prime of F inverse of 3. And now I can evaluate this outside in, or inside out, excuse me. I know already that F inverse of 3 is equal to 1. So I can replace F inverse of 3 with 1. And I can now find F prime of 1 by going back to F and computing F prime. So that F prime of 1 is, and F inverse prime of 3 is therefore the reciprocal or 1/4. So the key point about this is that to find F inverse prime, all I need to know is the value of F prime. But I need to know it at the matching point, F inverse of F. I'll see if